Welcome to PyData Global, Marcin. Marcin will be discussing today deep neural deduplication. Marcin is an AI architect with over 10 years of experience in various machine learning projects, including NLP and computer vision. So I'll hand it over to you.
Thank you very much. Okay, welcome everyone. Hello guys. Today I would like to tell you about deep neural deduplication. So basically the talk is how our team has leveraged deep neural networks and contrastive learning to handle a large-scale deduplication problem. The talk will be organized in the following way. At first, I would like to tell a little bit on the business case to clearly explain the need for deduplication. Next, I will provide a brief introduction to contrastive learning and then move to the description of our solution, explain how we scaled it up, and present the results and the next steps that we plan to perform. So let's start. Let's start with the...
Marcin, could I just ask whether you would want questions during the presentation or during the last 5 minutes?
I would prefer them at the very end because I believe that some of the questions that may appear immediately might be answered by the later slides. So let's keep them for the end of the presentation.
Thank you.
Thanks. Yep. So let's start with the business case. One of our clients is a company called Dodge Data and Analytics. And what they do is they fetch construction-related articles from all over the internet so that they are the first to know of new bits and opportunities. And what they do is they further share this information with their clients that are construction firms. As they collect the data from multiple different data sources, some duplicates may appear. For example, two different web pages may use varying words, different or incomplete data fields, but still refer to the same construction project. So to prevent Dodge customers from being presented the same information multiple times and offer highest possible data quality, there is a need for an effective deduplication mechanism. Till now, Dodge has been using a rule-based heuristic to produce a duplicate candidate for each new record. However, it's very, very, very hard to capture all aspects of what makes a duplicate with a handcrafted algorithm. Hence, such an algorithm was not quite accurate, and the results were further evaluated by data stewards. The data stewards, in parallel, used to spend a meaningful amount of time on identifying the duplicates manually. So that was a very time-consuming and error-prone process, and therefore it required replacement. However, this process has been in place for a long time. So there is a large data set of identified duplicates available. The dataset consists of several millions of records collected over the years, and each record has already assigned a duplicate if such duplicate exists. A record is simply a dictionary of named entities extracted from free-text articles, and there is a variety of them covering different aspects of construction projects, such as locations, dates, amounts, titles, names, and so on. Overall, there are several dozens of them, and we can distinguish two types of named entities. Text named entities, like project title or owner name, and numeric named entities like, for example, total square feet, latitude, longitude of the project's location, and so on. As we got access to a huge label data set, we could think of applying supervised machine learning for the deduplication problem. For example, we could consider building a binary classifier that takes as an input a pair of records and tells if they constitute a duplicate or not. However, this solution wouldn't scale up because for each new record, we would require pairing it with all the other millions of records in the database and then running such a huge data set of pairs through our classifier. And that would be definitely too time and resource consuming. Bestly, if we could simply transform the records into some points on a hyperplane and then measure the distance between those points with an ordinary distance metric that is easy to compute, like, for example, Euclidean distance. And ideally, if the distances would indicate the similarity, like small distances would indicate that there is a large similarity, and large distances would indicate that the similarity is small. So in such circumstances, we could simply project each new record onto the plane and just look in a small neighborhood to find if there is something. If there is, we got a duplicate. So to sum up, ideally, if we could learn such an embedding space where similar examples are grouped together and far away from dissimilar ones. And that's exactly what we can achieve with the help of contrastive learning. I believe that the idea of contrastive learning comes from 2005, but to be absolutely honest with you, I really got into it after reading the paper FaceNet from 2015. And even if this paper is already 6 years old, it nicely introduces many ideas and covers many aspects also applicable by more modern methods. So I will start with describing it over here. FaceNet introduces a loss function called triplet loss. And as its name suggests, triplet loss takes 3 kinds of examples: anchor, positive, and negative. So given an anchor example, we try to find another example belonging to the same class as anchor, and we call it positive, and an example of a different class than the negative, than the anchor, sorry, and we call it negative. And what we try to do with the help of triplet loss, we try to satisfy this equation. What means we try to make the distance between the representation of the anchor and the representation of the positive smaller than the distance between the anchor and the negative. And this might be converted to the following optimization problem. However, in this form, our model could easily find a trivial solution. What I mean is our model could simply transform all the input records into the same point, into the same representation, so that the distance between them is always zeroed, and this criteria is always satisfied. But that's not the goal we try to achieve. To prevent from finding this trivial solution, we add an extra parameter margin, and this margin parameter enforces that the positives are located closer than the anchor than the negative by at least this margin value. And this is the ultimate form of the triplet loss. In practice, triplet loss is usually used on a mini batch level. So given a batch of samples, we run them through a neural network, and we obtain a batch of embeddings, a batch of representation. And then among those embeddings, we select the triplets and add the triplets to the triplet loss. The question that may appear here is how to select the triplets. The most straightforward approach would be to simply generate all triplets from the mini batch and run them to the triplet loss. However, first of all, it would produce many candidates, and most of them would be pretty useless because the criteria from the triplet loss would be already satisfied, because the negatives would be already located further away from the positive and further away by at least this distance value. So in such case, the loss for such examples would be zeroed, and these examples wouldn't contribute to the training of the model. What is more interesting are hard negatives and semi-hard negatives. Hard negatives are negatives that are located closer to the anchor than the positive, and semi-hard negatives are negatives that are in between the hard negatives and easy negatives. It means that they are further away than the positive, but not further away than this margin distance value. So knowing what we are looking for, we could simply average the loss over all hard and semi-hard triplets. And this kind of approach is called batch poll. Alternatively, we could select the hardest positive and the hardest negative for each anchor. And this strategy is called batch hard. It's hard to answer which of them work best in practice because it depends on the task, and bestly if you could try both of them. Okay, so far it may seem like contrastive learning might be applied only in the supervised setting because we need to know the labels to create positive and negative pairs. But this is luckily not true, and we may apply contrastive learning also in the unsupervised setting. For example, we could follow the framework presented in this paper from 2020, where the authors suggest to use augmentation. What they say is that given an example X, we can randomly select some augmentation methods and apply to X what results in example Xi. We can do it once again and come up with an example Xj. And as Xi and Xj are basically the same example because they are just slightly modified version of X, we would like to make their representation similar. And this might be achieved with the help of normalized cross entropy. So given a positive pair of representation, Zi and Zj, that correspond to Xi and Xj that are just the altered version of X. So we would like to make those similar. Especially we would like to make it more similar to each other than Zi and Zk, where K are all the other examples within the same batch. So this is the positive pair and this is the negative pair. And the final loss is computed among all positive pairs in the mini batch. So this way we can apply contrastive learning in the unsupervised setting. I just presented two approaches, one supervised and one unsupervised, but there's way more to learn. However, that I believe that at this moment, all of you should have a good understanding of the basic concepts that will allow you to fully understand the method that we created internally in SII. So our solution, let's take a look. If you remember, I mentioned that we had two kinds of entities, text entities and numeric entities. So we decided to tackle the problem in a two stages approach and build two separate models. At first, we focused only on the text entities, and we used SBERT from Sentence Transformers package. This is basically BERT for text similarity, and we trained it in the following way. We took all text name entities and concatenated them into a consistent block of text. We just separate the named entities by the SCP token that is used by BERT tokenizer to distinguish between sentences. And then we used batch hard and triplet loss to train this model. However, we added a few modifications, and the most meaningful one is we modified the way we generate the batches. Because we dealt with millions of data records, and a single record usually had no more than just few duplicates, it was extremely unlikely that two duplicates would land in the same batch, even if we used large batch sizes. So we modified the sampling method in such a way that for each anchor, there is always a single positive example. And hence, we batch hard only the negatives. In the next step, we moved towards the numeric features. And here, we simply run them through a few layers, a feed-forward network with non-linearity, and then concatenate the result with the result produced by SBERT for the text features. And we run triplet loss on such concatenated vectors. However, in this case, we use SBIRD only as a feature extractor, and we don't backpropagate the gradients through it. We hope that this way we could explicitly teach the feed-forward network how to extend the vectors produced by SBIRD with this extra information contained in the numeric fields. For inference, we simply run a new record from both of our models. We concatenate the results to obtain these concatenate embedding vectors, and we are ready to compare this vector with all the other records in the database using a simple similarity metric. In our case, it's cosine similarity. However, this still doesn't scale up because we still need to compare this data record to all the other records in the database. So let's see what we did. Basically, to identify like the nearest neighbors, like I previously mentioned, that if we project the record onto the plane, we look in some small neighborhood. So to identify the nearest neighbors, we could perform an exhaustive search. However, the complexity of such exhaustive search is n times d, which means where n stands for the number of records in the database, and d is the dimensionality of the vectors. And as you can see, we had quite a lot of data records because at the moment of starting the project, there was 4.5 million of data points, and this number is still growing. And also the resulted dimensionality of our concatenated vectors is nearly 800 dimensions. So at first, we wanted to reduce the search space and not to compare against all n records in the database, but just some subset. And to achieve that, we could use approximate nearest neighbor search. For example, we could try to select 2 points from our embedding space and run a hyperplane through them, and in the next step, try to separate the remaining points according to the side of the plane they are located on. And performing this iteratively would actually build a binary tree, a binary search tree. In such a tree, the nodes represent the splits and the leaves represents the data points. Actually, we could even build multiple such trees and run the search in parallel to get further performances gain. And this is not really our idea. This idea comes from Annoy, and as you can see, we can reduce the number of comparisons logarithmically because this is the average height of the binary tree. So instead of running n comparisons, we could just perform log n comparisons. But Annoy is not the only library. There is more. There is Face, there is Flan, there is Falcon. They implement different algorithms like locality-sensitive hashing, like graph traversals. And among graph traversals, there is a very popular and powerful method called hierarchical navigable small words. So I encourage you to take a look. However, in our case, we didn't rely on any of the approximate nearest neighbor search approaches. First of all, Elasticsearch supports k-nearest neighbor search. It's implemented as an exhaustive search, and it allows to perform it on the embeddings. But what's the most important for us is that it also supports an efficient metadata filtering. It simply means that we can limit the search space by some criteria. And for us, it's rather unlikely that a newly published record will be a duplicate of something published like, I don't know, 5 years ago. So we just limit the results to the records published in a certain time range and perform the search among them. The second case, reducing the dimensionality, well, this could be handled with dimensionality reduction techniques like PCA, for example, or simply learning for smaller embeddings. And actually, in one of the next steps that we try to perform, we aim for the second option because we find it simply more elegant. What are the results? Okay, so at first we determined that the candidates produced by the previous rule-based heuristic, they were selected by the data stewards only in 43% of the cases, and the rest of duplicates was identified fully manually. However, we believe that still there might be many duplicates never found by the previous approach, because when we evaluate the predictions made by our solution, we can see that in some cases, the predictions are considered as incorrect, even if they look exactly the same or nearly the same as the input record. So we decided to still keep human in the loop approach to enhance this data quality by asking the data stewards to identify previously not found duplicates. And we want to present them top 10 results and ask them to identify duplicates among them. Hence, we use top 10 accuracy to express how many times a duplicate will be found for a record known to have a duplicate among top 10 predictions of the model. And as we can see, using just the text features brought us to the level of nearly 75% of top 10 accuracy, and adding the other features added an extra 10% points. So this is a huge gain in comparison to the previous algorithm, even if we still keep the human in the loop approach. And we believe that this is just the lower boundary of the performance for the reasons that I mentioned in the beginning of the slides. So what are the next steps? As I mentioned previously, we want to enhance the data quality before we move to a fully automated approach. However, as some of the duplicates are not identified, it also affects the convergence of our model. So we want to run our solution in production for a few months and then collect the data. We hope this the data quality will improve with the help of our model, and we will try to retrain our model. In parallel, we are working on improving the current NER solution by applying some state-of-the-art methods. And we also want to add more types of named entities to capture a wider scope of the project. And then we also want to shrink the size of the embedding vectors that we produce, but this is something you already know. And ultimately, we would like to train everything in an end-to-end manner to create a consistent framework for deduplication. Okay, guys, so let's try to summarize what I said today. At first, I would like you to remember and take away from this conversation, to this presentation, that contrastive learning is a representation learning technique that learns such an embedding space where similar records are located near each other and kept far away from the similar ones. And this kind of representation is super useful for information retrieval problems such as deduplication, for example, or for example, for semantic search. And obtaining this kind of representation might be achieved both in supervised and unsupervised setting. To perform efficient search among such embeddings, you need to consider two factors. The first one is the number of records that you are about to search among. And the second one is the dimensionality of your vectors. To reduce the search space, you can apply approximate nearest neighbor search, but as you could see from our example, it's not always necessary because sometimes you can incorporate like the domain knowledge to reduce the search space. Selecting the right approximate nearest neighbor method depends on your task and should be performed wisely. Before selecting the approximate nearest neighbor search method, you need to answer yourself a few questions like, how much RAM do I have? Am I just about to perform this search, or also add new examples frequently? But that seems like a good topic for a separate talk. So I will just finish here. Thank you very much. Are there any questions?
There are quite a few here, Marcin. So thank you very much for the very interesting talk. The same question looks like was asked by somebody in both the Q&A as well as the chat. Is it easy to calculate if triplet, easy, semi / hard? What should I do if I want to construct only semi-hard triplets for training?
So the question is what you should do to construct just the semi-triplets for training, right?
Sounds like it, yes.
Okay, so basically you should perform this operation on a mini batch level for multiple reasons. And it's basically just simple because in most of the cases, you need to go to do like the exhaustive search once again. So it means like compare all records against all the other records by some kind of similarity matrix, and then you can simply select what's being considered as a semi-hard example in your case. However, when I'm thinking about it, you could also try like more sophisticated approaches, especially when you deal with like large batches and you need to search effectively. But normally, what I think is done in most of the cases, and what we also did, is just calculating the similarity matrix and then selecting the triplets that meet the semi-hard condition.
Great. There was a question by Liv, but I think it was answered in one of your slides. There was a question by Stefan here. Oh, sorry. He's just posting a link to something with regard to ANN. There's a question by Jorge. Can you explain again who were the final customers? Why did they need the deduplicated records? He missed the context for the initial problem.
Okay, so basically, one of our customers is a company that operates on the construction market, and it's like a middle layer between the construction firm and the projects. However, if, for example, you want to get some information dedicated to your specialization, like you are a sink mounting company, and you would like to be interested only in projects that require mounting, for example, 4 sinks, and only from California and Florida, you can tell Dodge, please provide me with this information as soon as you get something. However, this kind of information might be presented in multiple places. So you, as a user, you probably don't want to be bothered like, I don't know, 10 times with the same information. So that's why there's the deduplication mechanism in place. And the second thing is simply the data redundancy. I hope this clarifies a bit.
Thanks. There was just also a few questions on what the ANN acronym means, whether it was artificial neural network or
approximate nearest neighbor search.
Approximate nearest neighbors. Yeah. Okay.
Yep.
Okay, I think that is the last of the questions. Does anybody else have anything else to ask, Marcin? One more from Brian. How do you deal with documents which might be about a few different subjects? Is it a composite score of some kind?
This is a great question, and this is on our roadmap to handle this kind of challenges, because we observe that it's not that frequent, but it may appear that there are articles that touches multiple different projects, right? So if we go for like a simple NER solution in this case, we'll have like, the same information and duplicated many times, like numbers of total square feet, numbers of addresses, and so on. So we are aware of this challenge. We are not handling it right now, but we are about to handle it. And the initial investigation and the initial ideas are mainly focused about co-reference resolution and grouping grouping the named entities regarding the sub-projects that are present in the articles. So hopefully, maybe next year, I will be able to talk how we dealt with that challenge. But this is a really good point.
Great. Thank you very much, Marcin. So we're out of time now. Somebody asked about a GitHub link. If anybody else has any questions for Marcin, if you could take it up on Slack, that would be great. Thank you very much, everybody.